You could just travel all over the world and try to visit every robotics lab and talk to the people there about what they're working on. Or you could listen to the Deep Future podcast, because that's what I'm doing. And I try to record these things and share them with you guys. So today we're hanging out with Rob Shepard. He's an old buddy of mine. I've gotten to spend a little bit of time with over the years, working on soft robotics and all the different kinds of materials advancements that could really help us make robots that are a little more naturally integrated into the world. And so he's had a lot of experience working on, the material science advancements that could make this possible. So things like polymer, colloidal suspensions as inks for 3D printers so they can fabricate microfluidic devices, synthesizing single micron to millimeter scale parts in glass and silicon and all kinds of other stuff. Think of like tiny gears. Imagine if you were trying to make micro machinery like Swiss watches, but smaller. That's the kind of stuff that he worked on in the past in research. Also developing pneumatic actuators, different kinds of elastomers and things that could maybe give us kind of muscles for robots, things like that. And then also developing the kinds of walking and undulating movements that you would want robots to do once they got beyond just being these kind of rigid, jerky things that we have now. So this also gets really interesting when you're trying to make fingers for robots, which I'm obsessed with. I think it is a kingpin that's going to enable robots to start going all the places they haven't been able to. We've seen some real progress on that lately. So anyway, look, Rob is a great guy, super humble, willing to share everything he knows, which is a lot. Rob is an associate professor at the Sibley School of Mechanical and Aerospace Engineering at Cornell University. We recorded this in Ojai, California, in the In-N-Out Burger on a Friday night when it was full of teenagers. So this is also an exercise in using AI for noise canceling post facto. I know it won't be the cleanest recording you've ever heard, but I think it'll be interesting to know that we ran the audio through a tool called Auto, AUDO.ai. And Auto is one of many. I mean, I don't have anything to do with them. I've talked to the founders a few times. I think it's cool. There's probably other ones. I don't know what the best ones are, but I've been using Auto, and it's able to do this remarkable job cutting out like 100 noisy teenagers while Rob and I are just sitting there eating burgers, talking about robots. So hopefully you'll learn something from that as well.
I've never met anyone like it.
He could hack anybody's phone in a matter of minutes. Who is that guy? Who can do that?
Thomas is the most interesting man in the world.
He's one of my favorite people on the planet. Inventor.
Wicked smart.
The master of cutting corners.
If you had a dead body in your trunk, who would you call?
He would get arrested immediately in a lineup.
I stood in line to get his autograph.
His mouth can barely keep up to his brain.
I don't actually know what Pablos does.
A hacker magician.
Man of the future. Future.
Had the same thing I experienced being from the Midwest and having somebody from California come.
Yeah.
They're always like, it sucks here. And then, you don't have an In-N-Out? I'm like,
Yeah, right.
I had a chip on my shoulder about it, but I've been here enough that I actually do really like it now.
I'm not even sure it's that good.
Did you ever go to 7-Eleven as a kid, like to play Street Fighter?
Yeah, totally. I went to, we had this game called 720, which is like the skateboard game.
Oh, okay.
And I played that one.
Okay.
I never got good at Street Fighter.
But they had, we call them suicides, and would just like mix all the sodas together.
Totally, yeah. That's same childhood, different latitude. If you go to a conference about composite, what's actually going on? Is it academics talking about some minute improvement to how you mix carbon fiber with other stuff, or are they like doing much cooler stuff than that by now? Like what's the state of the art?
These the conferences I go to are,
I mean, do you think there's like trends?
Yeah, like a lot of other, like material science, like any other physical science field, is like nothing new has happened for 100 years. So we're just rearranging a bunch of stuff. And so then there's like an existential crisis, and what should we be working on? And then so one of the movements is in making composites dynamic, meaning that they can rearrange themselves, self-heal, be integrated into systems, and how they can improve systems. Like So having compliant mechanisms is one thing. You were talking about that, I think, last week or a couple
Right,
weeks ago. And I was just like, oh my God, that's what I do. Yes.
Yeah, I don't know that much about it. So if we think of like the earliest composites were like cotton poly t-shirts. I mean, is the literal definition of composites two different together?
Yeah, but then it's like at what size scale?
Yeah, okay,
Because
right.
if you are an ant,
Yeah.
if you're a gorilla,
Mm-hmm.
then an anthill might look like a composite, but there are like
Yes.
several distinct things. So it's really what size you're looking at. And this is a philosophical discussion, really.
Yeah, right.
Are actually multiple different materials.
Yeah.
But people call them materials. And is it even worth thinking about or talking about?
Mm-hmm.
Academics do it because it's something to talk about.
Okay.
But I don't know. I mean, the thing is, what I'm interested in the composite space is pre-processing mechanical information to allow a controller to have a reduced set of inputs to make an informed decision about how to interact in the environment.
Okay, so what's a prime example of that?
A rubber foot on spot quadruped.
Yes. Okay.
Without it, it can't maneuver in the environment. Like all these control schemes don't work.
Without the rubber foot.
Yeah. We need to dampen the impact
Mm-hmm.
in order for it to work. And so,
Mm-hmm.
you know, what thickness should it be at? Should it be really thick or really thin?
Mhm.
What material should it be made out of?
Mm-hmm.
Our bodies have evolved over time. They're very particular thicknesses of
Right.
tissue on our foot,
Right.
based on the types of roughness and size
Sure.
scale of objects we interacted with. The arch of our foot, it has a. That's why some people have flat feet, which I believe probably for looked into it is some kind of evolutionary weakness that has been allowed to happen because now we have shoes and stuff like that. But
Mhm.
there's optimum foot thicknesses that allow you to handle rough terrain and things like that.
I remember
We don't notice it's a good thing. But you
somebody, the rash, when the barefoot running thing became a fad, someone described to me that the arch of the foot, think of as like an arc used to build a bridge.
Mhm.
And if, or like arches in, fucking Roman buildings or something. If you want to destroy an arch, you don't do it from the top, you do it from the bottom. And
Pushing up the keystone?
exactly.
Okay.
And the rationale is that in shoes, creating an arch is the dumbest thing because it's just destroying your foot from the bottom up. And so you should get rid of those. And I thought, oh, that makes complete sense. Then I wore barefoot shoes for a year and my feet splayed out and got like a size bigger. None of my cool shoes would fit anymore. But
I think of them more, but that's viewing them as like a static structure.
Yeah,
Whereas they're more like a spring.
probably right. And since I love wearing I actually put Birkenstock insoles in my boots because I like the arch. I
Uh-huh.
love the feeling of
Yeah.
having it fit. And so I gave up on the barefoot shoe. But I guess I wonder if you're a Spot. So if I look at Spot, that's kind of a weird robot because it doesn't have a foot, it doesn't have arch, it doesn't have an ankle, a joint. It's got like a knee and a hip and it's bouncing
Yeah.
up and down. It looks really weird
Yeah.
to me. Do you know why that is? Or
Well,
why? Is it just,
first of all, I'm a material scientist, not a control
Okay,
theorist,
fine, yeah.
but I have talked to people about it. Some of the funny things about these quadrupeds, and they're so useful,
yeah,
is that they're like, well, the control problem is solved, but it's only solved in the case that this is how the thing moves.
yeah,
And that can't be that efficient. In fact, they only work for like 90 minutes at a time.
Yeah.
Whereas a goat, which is a hoofed animal,
Yeah.
it doesn't have ankles,
that's a good point.
they can operate for weeks.
Yeah, so Spot's more like a goat than a dog, but just an inefficient one. Yeah, well, I don't see goats like
But it doesn't have
bouncing their feet around,
Hey,
not moving or
yes.
doing anything. Or,
Yeah, because it's what you said. They have ankles and they have
Yeah.
fine motors and all
yeah,
that
well,
stuff.
does a Spot extend sideways? It can't.
Oh, no, sorry.
It does not.
Yeah,
Yeah.
I think Animal does. I'm not so sure about Spot.
So,
I
like,
think it does.
Spot, if it's trying to like do a 360, has to like it can't do that. It has to do that in like the way a tank would do it. It's basically
Actually,
like
not sure.
it's like a tank trek version of legs because
Could be.
I don't think the Spot hips can
I
go
don't
sideways
think so either.
Yeah. Whereas
It
like
probably
a
is
goat
leaning
can.
over, like it picks
Yeah.
up and leans over and catches itself and
Yeah,
rotates
yeah.
that way.
And that's why it's doing so much do.
Yeah.
Interesting. Okay, so but getting back to the feet, the feet on the Spot, it's a rubber. I remember when I was a kid, there was like this TV show called That's Incredible,
I haven't seen it.
early
It's
80s.
incredible.
Yeah, it's called Incredible.
Uh-huh.
And there was this thing I got obsessed with when I was like 12. They showed this guy who had invented this rubber that he said it was like the absorbency of human skin. And it's called sorbothane.
Okay.
And the stuff is blue. And he put it on his hand and had a football player smash it with a hammer. And it didn't hurt him.
Wow.
It's like, half-inch thick. And you're like, holy shit, that's amazing. And then he shows like what happens with a normal insole, and like the hammer bounces and like everything shatters. And on like, a mannequin hand or something. And so that was the moment when I realized I got really obsessed with materials for the first time, because I was like, oh, you can make one that's bouncy or one that's absorbent.
Yeah.
And then even just, that was when I was like 7th grade. And then like, I remember like 5 years ago or something, I went to like a convention of like a trade show for shoe companies. So it's all the people trying to sell stuff to Nike and Adidas. And this was in Oregon. And so there's like entire companies who just sell laces.
Wow.
And there's like another company with a booth that just sells like the eyelets that the laces go through. And then it's like another one that sells Velcro straps. And there's like all this goes. And then I found this company that sold the cushioning materials, thermoformable foams. And they had one that was bouncy and one that was absorbent. And their demo was like drop a steel ball on each one. I thought that was so amazing. I bought some of this stuff, which I still have and have no use for, but I think it's cool. Anyway, so the point is, but I didn't know. Like, I don't know what's better.
Yeah.
Do you want the foot of a spot to be bouncy, or do you want it to be absorbent, or a mix of both? Or like, what? I don't actually know. It's like, was so non-intuitive. I realized to figure out, I'm like, well, maybe I don't want my shoes. It's probably slowing me down.
Yeah.
If I'm basketball shoes, maybe I want them bouncy.
Well, it's very different. In the case of spot, you want to dampen the impact.
Yeah. Cause you want that foot to connect with something for a little bit.
Right. Yeah. You don't want it to just bounce back up.
Yeah.
And you can also, there's some elastic energy storage that they're putting now into the leg farther up and things. But the very first thing to do was to put rubber on the bottom of it. And I went to somebody's lab and they said, look at this. And they threw the rubber against the wall. It hit the wall and then it just fell on the ground. Like, that's awesome. Now, in biology, I don't think that would be awesome, because I think you want to store as much energy as possible and restore it to the environment. But our solutions are, let's get rid of the energy so that our controller knows exactly what to do.
Right. So we're not at the point yet with most robotics where we're efficient enough to like reclaim and store the energy. Yeah. Whereas like
they're starting to do it. They're starting to do it in like spring dampers but it's much more, it's inelegant compared to how we do it. Like they have like a spring and a damper, and based off of like their particular geometries and architectures, they'll have more elastic energy storage and more damping. Whereas we do it again through composites, through mixtures of material properties at the millimeter scale, distributed everywhere throughout the body. So we can do it in 3 dimensions. And so like if the body is twisting this way normally, then we'll have our composites designed for that. Yeah. We have one of the things in one of the episodes about you were hypothesizing why I think fingers or hands or something don't.
Probably fingers.
And one of the issues is also that we can distribute muscle. Well, biology distributes muscle at the millimeter scale. Motors, like even small DC motors, are still centimeters big. And then how do you wire them? You have to get all the wires to them everywhere. So biology, because we can grow everything from the bottom up, we can have infinite complexity compared to our human technology. So you can wire everything. You can have you can have these fine-tuned details that we just can't do right now.
Yeah. That was one of the things I was trying to figure out. What's the state of the art with this stuff? Because there's 2 things. One, think of a muscle in a mammal. They're like thousands of tiny muscles stuck together, which are independently controllable. And then if you think about how we do it in robots, there's no robot that seems to be like that yet. And we probably need that in order to be able to get to the level of sort of resolution and movement.
You brought up a Festo Gibbon actuator, which is awesome. It is, as you're saying, a contractile actuator.
Contracts.
And there's this person named Koichi Suzumori, and decades ago, he started using them to make robots. Okay. And over time, he was focused on that and is adding more and more of them per, cubic meter. And then he has this robot demo. Like, I think it's a humanoid or a biped anyway.
Yeah.
That has McKibben variable recruitment McKibben actuators. So a bunch of them, and you can recruit some of them or all of them, but it's like enormous.
Yeah.
And the tubing is everywhere. And it's just like that.
So he's using the like Festo pneumatic muscle.
I think he makes his
something
own.
like that.
He might buy them, but I think he makes his own.
Oh, he makes his own.
Yeah.
And then it's just, so he's making a humanoid that's like a Michelin Man bundle of.
Yeah. But the
soft
vision
actuators.
is that is the android in iRobot, the movie, you know?
Yeah.
In that movie, there are McKibben actuators.
Oh, interesting.
Operating that.
Oh, that's what it's called.
Yes.
The contracting pneumatic muscle.
Yeah.
I see. Okay. And so if you could have anything you would want, you would probably want something that's like millimeter scale.
Yeah.
And with a wire coming out each side and then like thousands of them bundled together, and you could replicate a bicep. Yeah. And then you could start to make everything robots have.
But the details of wiring it is like fucking hard.
I mean, it's not as hard. I mean, on boards, you know, like it's a lot.
Not in 3 dimensions.
Not in 3 dimensions.
Like, and yeah, maybe you could do it. Yeah. Yeah.
I've had 2 companies recently pitch me on their own inventions for something like that. And I don't know how good they are.
Okay.
You should maybe take a look at them.
Okay, sure.
Yeah, I'll send them to you because I don't know enough to know what window of utility they're in. And it wasn't clear to me that these would be technologies that you could justify making a whole company out of it. You know, it's less a fefeature than a product.
Right.
Which is the real problem with a lot of inventions. You know, it's like the invention doesn't map. It's not no slight against
Have one of
inventions.
those.
They just don't map to the status of venture capital and how we do that. Oh, so here you have one that contracts.
This isn't a muscle. This is a sensor. You
It's a
were talking
sensor.
about the difference between a platform and a.
Oh yeah. Oh, it's
and
a product that.
So this on this side, these are stretchable fiber optics.
Oh,
that
okay.
The company makes. They're basically very high signal to noise ratio strain gauges, in the
Okay.
order of like 60 decibels, which is like
Yeah.
Bose quality versus like the headphones you got in the 80s.
Okay.
That's sort of like what the competitors are for stretchable strain gauges. So they're so sensitive. Like, what should we do with them? Well, one thing we can do is disambiguate multiple confounding mechanical inputs.
Okay.
So this is a cardiorespiratory strap,
Oh, okay.
and it measures tidal volumetric lung information, not just rates, but tidal volume.
Okay.
And we notice we can see heartbeat on it too, on the fibers. So,
Yeah.
and you can do it through clothes. So you don't need to actually put it on your skin or anything.
Well, it needs to be tight around you though.
It has to be kind of tight. I mean, it doesn't.
Yeah. I mean, it has to be. Yeah. Okay.
Yeah. It's no more, it's actually even less tight than the ECG type monitors.
Yeah. Oh, okay. Cool. So it's like a modern G.
It's a ballistocardiogram,
Oh, cool.
because the heart, it contracts so fast and it pushes blood so fast. It creates mechanical vibrations that we can detect with that. So this fiber, each fiber detects both the ballistocardiogram as well as a chest excursion. And because the signal to noise ratio is so high, we can see those waveforms.
Can I post a picture of it?
Yeah.
I'll take a picture of it and
But since the signal to noise ratio is so high, it's not just
with fries.
that we can see. This is what, it's for the people we come in doing that. They're like cyclists that care so much about their body. And so we have them come in, but we get them to come in because we do free VO2 max testing.
Okay.
So they put the mask on, they put this on, they get their VO2 max, we get their data and correlated to VO2.
Yeah.
And now they can do accurate VO2 data without the mask.
Right.
But then,
I see.
So it's like, should we do a strain gauge and then sell to a bunch of people? Should we make a product out of it?
Yeah.
And then we decided that because of the high signal to noise ratio, you can also sample really fast and still make sense of the data. So we sample at hundreds of kilohertz.
Yep.
So now we have contact dynamics for things like,
and you can see me breathe. You can really see, like, if I'm breathing into my, that's me. You could see if I'm breathing into my lungs or down in my belly.
Yeah.
Or Okay.
Oh, it's a serious right.
It's right, my turn. Sure, it's what was the angles?
I'm just going to calibrate so I won't be able to talk for just like
Okay.
10 seconds.
Yeah. Okay.
That's right.
That's right. I have masses. What is that?
I was I was on the way from.
I love that. I just stopped by a couple of days.
So that's the,
Okay, so I'm seeing you breathe right there.
yeah,
This is the big chart is your inhale, exhale cycle.
that's right.
And then it's showing heart rate, respiration rate, ventilation.
Yeah.
Cool. All right.
And ventilation, which is the
And-
big difference, because like on people's watches and stuff, you can get heart rate
Mm-hmm.
and respiration rate from photoplethysmography, but the volumetric stuff you don't.
Mm-hmm.
And
So
even
it's mostly useful for athletes and medical applications, I guess.
yes, that's what we're going for. Mhm.
And then, but you probably need like a company that's in that business already to just use this
But,
instead of the way they're doing
You know,
it now.
I'm new to startups and stuff
Yeah.
like that, so just telling people, oh, it should work for that didn't work. So we had to make the device.
Right.
And so we're going to try to get some initial revenue and then say, oh, look, people like it. And then move on to other things that we also are good at, like contact dynamics, like from shoes,
Okay.
golf club handles, things like that. And then,
So for that, the people who want to use it, you think of like a company who's making the old and busted version of the device.
Yeah.
They just want to buy the part. They want to buy the sensor and use it.
Yeah.
And we have a cool sensor, but the companies who make sensors in the business of manufacturing
Yeah, that's
a whole thing, getting it certified, CE, all that shit, and then trying to get it picked up by product manufacturers. And so it's really hard to do that. I think it's really hard to do that for just a company with a product, essentially,
what we have done
Mm-hmm.
is develop a pretty sophisticated signal processing workflow
Mm.
with very special algorithms to interpret this data.
Oh, so you need that too.
Yeah. And I'm not sure we would like to partner with another company in each of these specialized verticals, but I don't know if any of them help us really. I mean, they have expertise in it, but they don't know how to do what we do. Like all these companies,
Yeah.
I'll use the PPG based ones again, the light into the blood and then the measure the reflectance to get. None of them have their own sensor. They all just said, we're going to develop the algorithms to use this sensor for this particular thing.
Yeah.
And now there's algorithms that you can download from GitHub to do that stuff. And so all these other companies can come out and they can start competing and doing all these things, but ours don't work. You can't use those. We're the only ones that have that.
Oh, you think it's not possible for other people to make a,
Oh, they can. They could.
Yeah.
Much as IP is defensible, we have a fair amount of IP on those fibers and the integration, the optoelectronics, and then the algorithms, we keep them secret.
Yeah.
Eventually someone will figure it all out, but how far ahead can we get before that happens is the thing. And it's sort of, and so back to the conversation about robots and all that other stuff.
Yeah.
I developed those sensors for robots because almost all robots just use vision.
Yep.
There's encoders in the motors to tell how far the motor's turned or something, but it all assumes that nothing has happened to the legs. Like they're all the same shape.
Right.
And that's hadn't dented or twisted or anything in any way. And then vision can't tell if the rocks that you're standing on have moved underneath you. If you look in nature, there are many examples of animals that are blind, but I don't know of any example of an animal that can't feel. I think it's a more important sense than vision for agility and mobility.
That's super interesting because we're at this point now where vision is performing so well in computers that people are sort of running amok with it. And, we were talking about this the other day, the obvious example is like Tesla is trying to do everything with vision and get rid of all the other sensors. And I think that's probably a cost saving measure on their part. But if you had price sensitivity, then you would also use LiDARs and whatever else you could get. But they're not doing that. And their rationale, which seems sense that human driver is only using vision, which is like probably 99% true. And so,
but the roads have been engineered to be flat and predictable. Trillions of dollars spent on that.
Yeah, trillions of dollars in engineering the environment to be safe for a human driver who's only using vision.
Yeah. And
so
you brought up an example as well of the lab that has a camera to measure touch, the rubber front and
to make fingers for robots, basically using vision, but adapting that to other senses, which seems really interesting. I mean, what do you think about that?
Oh, I think it's great. That's what we do with our fibers. It's seeing touch just in a different way. So they have like a CMOS, and then they're scanning the pixels to look at how the attenuation of light is changing.
Yeah.
Another example of that is Puyo, this Toyota Research Institute.
Okay.
It does this, and it operates kind of the same way. But how
does it operate?
It has a camera, and then it looks at how the rubber sphere is deforming. And then there's this other company called GelSight out of MIT, which isn't a hand, it's just like this rubber pad.
Yeah.
And it's also the same thing.
It's a pad with a CMOS sensor in it.
Yeah. And it looks at, and there's a silicone gel in the top, and I think there's a metal film on it. And as you press on it, it's like reflecting light off of it internally. And it's something like that.
Yeah. Cool.
Yeah. And so I've learned all about this stuff. One, because I'm very interested in adding touch to robots. Two, because we're, working on these fiber optics, which it's the same thing. You're seeing touch. The difference is in that case, you have one chip and it's localized. We send our light to where we want to touch, where we want to feel, and then send it back to the same thing. So
you have like one CMOS sensor with fiber optics spreading out.
We have an even shittier thing than that. Like, it's just like a few photodiodes.
Yeah. With fiber optics going around a robot or whatever that you're trying to.
Oh, he's sitting down at the yacht.
And how much is possible doing that?
I think it depends on what you want. So the resolution, it's an extremely high speed, extremely low resolution camera, like a few pixels.
Oh, okay.
But we can do it because we're sending light to exactly where we want it physically by placing the fiber optics there. If you don't do that, then you need high resolution so you can pick up everything.
Okay.
But if you have high resolution, you also have low frame rate. So you can't sample things very quickly in those cases, the CMOS based cases.
How quickly do you need?
Well, that's our value is that before high speed cameras didn't know, I mean, maybe people did know, but it became so revealing how fast many things actually are. I don't know. I always think about the cannonball hitting that guy. Well, no, it's like some kind of circus trick, and it's probably very low power. But then you like see his body all rippling and everything like that. Before. So, and when you're a baseball pitcher, the fastest motion that humans make first is javelin throwing.
Okay.
And that would make sense from an evolutionary perspective. Second is a baseball pitcher. Their shoulders rotate at something plus 12,000 degrees per second. And their angular rotation is like 1,000 meters per second squared. They get to like 100 Gs. You cannot measure that with high-speed cameras because even though high-speed cameras can measure at 100,000 frames per second, they can only do it at low resolution. So try to capture the person doing that in all the different places. You can't. So it's a contradiction that we solve by placing the light where you're measuring.
Okay.
With something like 10 photodiodes.
I see. I really thought that humans were much slower.
Exactly.
Okay.
Yeah. And I bet there's so much more to reveal about animals, people, machines, these kinds of.
They've got these shrimps that are doing sonoluminescence and whatnot, or cavitation-based luminescence.
Yeah, those mantis shrimp.
Yeah.
There was a DARPA competition that funded, I think DARPA, there was maybe it was ONR. We didn't win. We were competing for a grant. This other team won and I was like, wow, that's really cool.
They were doing something with the mantis shrimp?
Yeah.
It's all about the science.
So
Be honest.
if you had a good budget, you would make a robot like Spot. You would send fiber optics out to all the joints, maybe even feet all the way across all the movable parts.
Not only the movable parts.
Oh, and everything else too, because you want to know if things break or bend.
If it hits, if the terrain underneath it is moving, wall, all that stuff.
Okay, so you'd want to basically have like
skin,
like a skin. You'd have fiber optic, at least in your architecture, you'd have fibers going to like every centimeter or something on the surface of the thing that you could sense what's happening there. Wow. And certainly with like a modern CMOS sensor, it should just be able to like grab a bundle of fiber optics, glue it to the CMOS camera or sensor, and then just, string the fibers everywhere. I mean,
We did that.
you did that. Okay.
Yeah,
All right.
we did that. The cost was frame rate.
Cost is frame rate because the CMOS sensor's frame rate is too low.
Right. Well, it's too low for some things,
Mm-hmm.
but for the normal kinds of slow touch we think about, it's okay. But to slip, that's really fast. It can't do that.
What if you need a sub?
But if I have cost, it's still pretty low res. If I had 1,000 fibers, that's like 1 kilopixel camera. That's like from the 80s. And then if I had a modern new, the frame rate was like, I don't know, 1,000 frames a second. That's not crazy. 1,000 frames a second times 1,000 pixels is not a lot of data.
Yeah.
Seems like that could tell you a lot, right?
Yeah. I think you're arriving at maybe even better than what we're currently doing, but not too different.
Okay.
Because the fibers themselves have a finite diameter. So you can't have 1,000 of those fibers.
Yeah.
Right. So you're going to have to spread out the pixels anyway.
Mm-hmm.
And so then you end up with kind of individual photodiodes that you're sampling, which is what we have.
Yeah.
Another cool thing is the acceptance fields mechanically.
Yeah.
So these fibers, they can be influenced by touch that isn't directly on them if they're embedded in a rubber.
Right.
So you press here, this fiber's affected, that fiber's affected.
They're pressing
depending
between two
proportional-
fibers.
Yeah.
Yeah, that makes sense to me.
Mhm.
So maybe centimeter resolution is enough or something like that, or less than, my sub-millimeter resolution. That's like, and basically you're describing what a human body does. Like you got a brain, it's got a bunch of axons.
Yeah.
They're like connected to little spots all over your body.
Yeah.
And they feel shit and send it back to the brain.
Yeah.
So like, it seems like it ought to work. The closest to like a fabric or an off the shelf thing that you can make or have seen, it could be the skin and plug it into a chip and go.
We print rubber lattices using DLP and then thread the fibers through the porous rubber. And so
Okay.
basically whatever you want to wrap it around,
Yeah.
you just print that porous framework like a sock,
Okay.
put it on with the fibers.
Right. Okay.
But none of this, the high speed,
Mhm.
it doesn't matter if the robot can't respond to the information fast enough to matter.
Right.
So these motors, they don't have the speed to compensate for things like high speed footfall slips or anything like that. So that's one of the tricks that we're working on now. And on that side of the things, we don't have a commercially practical solution. We use microcombustion. So we make little millimeter cube rubber balloons
Mhm.
with gallium electrodes that
Okay.
are sort of liquid, so the whole thing is soft. And we flood the skin of it, a bunch of these bubbles, with a bunch of electrodes that we use a shift register to individually address. And then based off of the sensory input, we compute which actuator array we should combust. And so then we can have less than a millisecond sense compute response times. So we call it bang bang. So you hit, explode, and
I
then
like that.
yeah. The digital part is it takes the longest time. So we created analog circuitry to do some of the computation. Sometimes it works, sometimes it's not sophisticated enough.
Wow. Bang Bang is the name of one of the characters in one of my favorite movies.
Really? Awesome.
Yeah. It's called The Brothers Bloom.
Okay.
It wasn't big, but it's a really, really ingenious, like super creative film.
Okay.
I love it. You got to
All
watch
right.
it if you watch movies.
Yeah, I do.
The Brothers Bloom.
I'm almost done watching all of Battlestar Galactica 2004. It's like the third time.
Now you're way ahead of me. I only know that one movie, so I recommend it. No, movie's a long time ago. Okay, so you've seen the modern 3D printers that print they have like a spool of carbon fiber thread, and they can put that thread down and like wind it into shapes, right?
Wind it in. You mean like the Mark Forge?
Yeah.
Yeah.
So what if we took one of those, got a spool of carbon fiber and a spool of fiber optic?
Yeah. Oh,
And we can go lay down these fiber pathways inside of a 3D printed thing for you.
I like it.
And then the fiber optics have to be terminated somewhere, but
That's awesome.
wouldn't that be
That's
cool?
great. Yeah.
What about just
I
try
would
to
say
think
that's good for the stiff
stiff stuff?
for like compliant, but not deformable. Not, yeah. It's not.
Well, in theory, though it's making Well,
for a robot, it would be a good
carbon
idea.
fiber is basically there to make things stiff, but
Yeah.
you could replace that with something that was less stiff,
Yep.
a binder that was flexible.
Yeah, I think it's a great idea.
What about, I mean, it seems like the ultimate thing to get to would be like a fabric that I can just cut into pieces, almost like like wrapping a car.
Yeah.
Just like heat a car
Mhm.
with some fabric
Mhm.
that would have one of your little bubbles, millimeters or something in it.
Well, that's the force.
Yeah, I sold
And
that.
then
Yeah, people,
they need some way of, we need some kind of like network
Finals.
signal out.
Yeah.
Yeah.
I love the idea of using constructive, destructive interference of things.
Okay.
Like,
Yeah. Right.
I mean, this sonoluminescence thing. I mean, there must be a way to trigger acoustically these reactions without wiring, and then that would allow that to happen. It's a bit far stretched from my expertise,
Yeah,
so we
yeah.
don't do it. But I think it's
Yeah.
what could work.
Yeah. We just really need some kind of practical
Did you send Yale beating Walbert?
mesh network. Like, what do they do for, like if you have a OLED display
Mhm.
and you shoot a hole in it,
Mhm.
all the pixels that didn't get blown away will still operate.
Mhm. Mhm.
So they're not doing the normal
Yeah.
scanning matrix behind a TFT array, I
Right.
guess. But I don't know how you address pixels in a OLED display. There's got to be some, I don't know. Anyway, somebody should
Yes.
tell
All right,
us.
get
how
on
do
that,
you,
people.
How do you make a non-destroy matrix so that you can address these? Because you basically at this point know how to make a pixel that can feel.
Mhm. Yes.
And what we need is a practical instantiation of that where we
Yeah.
can wrap those pixels around anything we want
Yeah.
and feel when stuff happens. Like
Maybe.
that's-
But what is the
Yeah.
scale of the thing we're talking
yeah.
about?
I mean, if we wanted to make robots that feel like humans do in human environments, and
Yeah.
stuff like that. So, okay. So that's one. So then if you wanted to do that we want to make synthetic ants, then almost
Yeah.
in some sense that seems like easier.
Yeah.
It's just like less surface area to feel on.
Yeah.
I don't know.
Yeah.
Mm.
But then the optoelectronics are they actually do it. They have a finite size, and then
Yeah.
the wiring, and then you need a controller, and then the power, which brings you to another topic I'd like to discuss is as you scale things down,
Yeah.
batteries are worse. The packaging to volume of the packaging to the active ingredient of batteries doesn't scale well as you go smaller.
Right.
So powering an ant size thing becomes extremely difficult. So we've done that again with combustion, but this is just a segue. It's a bad one. That's what we really do is work on multifunctional use of batteries, of liquid batteries.
Okay.
So for hydraulically powered robots, if you make the hydraulic fluids
Yeah.
electrolyte, then it also is the battery.
That's
Yeah.
interesting.
Yeah. And so we do that for underwater robots.
Oh,
So then the more liquid you add, the more capacity the robot has, but at very little cost. So we could, and we're making a 3-meter long robot based off of something called the oarfish, which was sailors thought they were sea serpents, but they're actually oarfish, and they're just enormous. And by filling it with liquid and having that liquid pressurized, it forms the stiffness necessary to do the anguilliform type motion to cause it to swim, but 90% of the weight is the battery. So it can, in theory,
the
operate
same liquid is part of a liquid battery.
Yes. You can do other things too with it. You can thermally regulate with it. So you can, and you can also communicate wirelessly through the ions in the electrolyte.
Oh, so your battery fluid is the hydraulic fluid, is the coolant, and is the control
Data. And the power too.
That's super cool.
Yeah.
Wow. Great idea.
Thanks.
I like that.
That was a genuinely bio-inspired idea.
Yeah, I like that.
I just thought I actually had this program manager who really didn't like pumps. Like he liked biomimetic robots, but a lot of the soft actuators use pneumatics. And he's like, I don't really like using pumps. So I came at him with, all right, I got to solve this problem. Our heart is a pump. Like pumps work biologically, but then they're pumping things that are not just transmitting force. So like, what does a heart do? A heart transmits energy, and then the energy is used distally by muscles.
Right.
So how can we do that? And so that's how I sort of arrived at this. I initially called it robot blood because it's cool.
Well, it's transmitting. Yeah. So heart's transmitting essentially fuel.
Yeah.
There is a cooling It is a coolant,
Yep.
but it's materials
Yeah. Mm-hmm.
as well.
Yeah.
Yeah. Interesting.
They're all
Yeah. I mean, I think if you just keep going down this path, you're just going to end up, recreating all the things that biological entities do.
That's why I love that.
They did.
The humans created versions of themselves and then they took over. But yeah, like the normal trope.
The ones they created took
yeah,
over.
Yeah.
Yeah. That seems like a tired trope at this point.
Yeah.
But
what's cool is that they look like people, but of course I don't work on intelligence. So the only thing we do is work on the bodies.
no, it turns out that was harder.
Yeah,
No.
I guess so. I
yeah.
guess there's less
No,
money
the
going
jury's
into
still
it too.
out, believe me.
Yeah.
So when you think about soft robotics,
Mhm.
would you say like 90% of what matters in the field is just feeling?
Well, it's mostly actuators and sensors.
Yeah.
The sensors are actually the easier thing to do
These days. Yeah.
You're inputting energy and you're interpreting it. Whereas the actuators, you have to output a force, and then the energetics involved are less efficient, and it's hard to do. We work on it, but we just work on the mass transport issue, which is what the combustion really solves. Like you're sending a little bit of mass,
Mm-hmm.
but then you rapidly expand it.
Yeah.
So the blood thing, you brought up an example, you're transporting mass. That's a hard thing to do.
Mm-hmm.
You have to send blood here from your heart, your chest, to all these little tiny regions all throughout the body. We can do it as organisms because we've grown up these capillary networks from the ground up. In order for us to do that artificially, we need to do things like additive manufacturing.
Right.
And even then we won't get to the same Murray's law type efficiencies that biology has.
Mm.
But one of the quotes I really like is additive manufacturing is complexity for free. The same amount of time it takes to print a brick, you could print a tree.
Yeah.
So we try to apply new additive manufacturing technologies to building biomimetic robots. DLP was really good. The basically projection lithography, one image at a time builds up. So instead of the FDM, which is like a curvilinear type path planning thing, projection stereolithography is a plane at a time.
Yeah.
So it goes faster. You have costs there. You can only do one material at a time usually. And then there's a new one, volumetric additive manufacturing, which is like inverse tomography. So instead of starting with the 3D thing and then getting the images out, you start off with the images and you project them together to get the volume.
Because they're coming, so that you project from multiple sides.
Yeah.
It's kind of like stereolithography, but instead of doing it with a couple of lasers, you're doing it with a couple of images.
Yeah. The effect is the same.
Mhm.
The physics is different, but and it was invented a collaboration in Lawrence Liver Laboratory and Berkeley. And we've okay, that is awesome because you can print objects in 60 seconds that normally would take hours to print otherwise.
Okay.
At this time, it's kind of small. We've managed to get the optics and things bigger to print bigger things, and we switched from just hydrogel material to silicones. So we're getting it because this is all stuff we need for the robots to work. Most of the people are working on tissue engineering applications and stuff like that. So but our focus as robots allows us to do expand the boundary conditions towards what's useful for robots.
Yeah.
And that should allow us to do mass transport better.
We tried this thing one time. This is a long time ago, so I don't remember the details, but I think it was my buddy Eric's idea. He took resin and then dyed it red, green, and blue, and then dumped together in the DLP type printer. And then using RGB, he could cure different colors of it to make like an image. It didn't work great, but it sort of worked.
Yeah. You're trying to solve the multi-material issue.
It was a way to solve multi-material. And presumably, I don't know, but maybe that could be applied. I don't know if anyone's tried this. That could be applied as a way of using that type of printer, but to get multi-material. So you get different resins that cure with different wavelengths.
Yeah.
This was kind of the budget version. We did it, in HackerBot Lab just to fuck around. But you could imagine making a version where you just have resins that have different properties that cure different wavelengths, and then using that thing, you could go make very complex structures.
That's awesome.
I haven't seen anything like that.
Commercially, no. My former student, TJ Wallen, he just started MIT in material science. He's doing orthogonal chemistries. So different wavelengths trigger different reactions.
Yeah. Okay.
And so you can do that. It's effectively what you were doing.
Okay.
Just probably more fine tuning on the chemistry side of it.
Yeah, cool.
Yeah.
It's weird to think that nothing biological is 3D printed.
Yeah, I know. Well, people have been working on self-assembly
Yeah.
in material science for a long time, and it's just so hard to do anything complicated. You can self-assemble things like Langmuir-Blodgett films or like Bragg gratings and stuff, but not any useful machinery.
Probably very unlikely to get a lot of attention, since at this point you'll just get a lot further with engineering biology to do it for you.
Right. Yeah. We have a paper coming out. Well, I shouldn't say that, it's in review, but we use a mushroom,
Okay.
the mycelium of the mushroom,
Yeah.
to sense the environment and control a robot.
Oh, interesting.
Yeah.
And how much sensing can the mycelium do?
Well, it's very sensitive to light.
Oh,
They don't like light. So
Mhm.
if it goes, so one of the programs we constructed is to have the mycelium, which issues action potentials that with enough signal processing, you can start to coarsely understand it. So like, depending on what it's experiencing, it'll drive the robot forward. It's basically embedded in a untethered wheeled robot. So it'll drive the robot forward. And then if it sees light, the action potential waveform changes and it says, oh no, and it goes backwards to get away from the light. It's also sensitive to gases like CO2 and
okay.
probably maybe some hazardous chemicals as well. Mushrooms are really robust against, I think there's mushrooms that eat radioactive material.
So how much have you seen people trying to adapt sensors for robots? I mean, it seems like there's a shit ton of possibilities because biology has evolved sensors for almost everything anyway.
Yes.
Why can't we just start co-opting them, grow mushrooms on our robots or fish eyes or bumblebee eyes or spider eyes or I don't know, whatever is useful.
I think the biohybrid robots or engineered living materials, this is there's a lot of focus on that now.
There is,
Funding's going to it, yeah.
Especially now we have like the organ on a chip abilities where we can start to put on chips, instrument them. Seems like that's what you would need to turn biosensors into something useful for a computer.
Yeah. No, I mean, it's the future. Unfortunately, setting up a lab to do these kinds of things is really expensive. I've sort of committed my direction into artifices. We started using mushrooms because I was like, how can I get in on this? And mushrooms are cheap. Like it's hard to kill them.
Right.
So you can, any lab can set up a mushroom facility really cheaply. So that's why we started working on it.
Okay. Right. Whereas you don't need
but we're able to learn things that I think are going to help other people, and that, all these things die. So if you're going to have these instruments, how do you deal with death? The signal is going to change as they age. Can you rejuvenate them?
Okay.
These things like that. And that requires hardware solutions.
Sure.
So we're working on that.
Feed them.
Yeah.
Got to keep feeding your mushrooms.
Yeah. Send new spores in, regrow the spores around the electrodes. We use the same kinds of electrodes that are used in neural interfaces. So signal processing, we can learn from rejuvenation. We can learn from, I don't know, even if the mushrooms themselves end up not being useful, which actually I think they would be for sensing applications, they're not actuators. Yeah. Which is what most biohybrids are, at least in robotics, are used for. Most people are like, muscle's really good. Let's just use muscle from a rat or something. Right. And that's, been effective. Yeah. There's Kit Parker at Harvard has this manta ray like thing he made out of cardiomyocytes. And then I think optogenetically modified, so you can pulse light on it and control it that way. Yeah. Yeah. So lots of people not lots of people, but very few very good people are working on lots. I've been to money for lots.
Kit's lab. They are doing super cool stuff there. I didn't get to see the manta ray. It
was a bit older, I don't know if it's anything like my lab. Yeah. Once you've demonstrated the results, you take everything apart and reapply it to something else.
Believe me, I know how that goes. Like, we had a manta ray, but it got
now it's a porcupine.
Yeah, exactly. Yeah, take what you can get.
Yeah.
What do you think is I guess this is kind of what we covered, but like, what's the state of the art for fingertips? Like, if I wanted to make a fingertip for a robot, in my like, how would I do it?
I would use those CMOS cameras with rubber at the ends.
That's the best we got.
I think so.
Do you think that there's an exciting robotics now that comes from the glut of computation that we have? I mean, mobile made chips so low power and cheap, and now we have extraordinary compute abilities. We could even be making, I mean, I don't know, but I presume we could train models on supercomputers and load them onto robots to run. I mean, is that kind of the direction you think we'll go in? Because we have such vast supercomputers now and more coming
I think so.
to the training in a
Students are really interested in
giant
it too.
simulation.
So as a hardware person,
Yeah.
it's a bit frustrating that my graduate students are always like, I want to start doing machine learning
Yeah.
and stuff like that. I'm like, can you please make this hardware? And instead they take a bunch of classes too. So it's good and bad. I think that actually will reduce the rate of hardware development because everybody's offloading the work onto computers. And sometimes like I'll go to some conferences and everybody's like, all we need is vision.
Yeah.
What are you talking about? You know?
Right.
And I don't think that's true. I mean, but right now everybody's trying to dump everything into computation and cameras. And I think you could do a lot with touch sensing and maybe less computational.
Well, I think the kind of the, conversation I had with Riyad Benisman is like, can you have, vision is not a very, I don't know, semantically inaccurate. So vision is like on one part, it's sensing optically, but the processing for vision, which is the important part of computer vision at this point. I mean, they're both important, but and like the gummy finger is an example of taking the processing from vision.
Yeah.
And I guess we are using the sensor from vision too there, but you could jettison that. I mean, I could use a bunch of microphones, but then that audio using vision algorithms.
Yeah.
And
brain, I think, does that too.
I think are doing that.
Yeah.
I mean, more and more, I'm just convinced that the brain is using vision to process everything.
Yeah. And that's
it's
why
using
something to process vision. It's
using something to process everything. And it can do vision. It can do other things.
Right. What's the name of that 3D model of the person with everything magnified based off of what the portion of the brain is?
Oh, I don't know what that's called.
Oh, it looks homunculus, I think.
Homunculus.
It looks hilarious. But it's supposed to represent like the hands are really big because of touch sensing. And I think the tongue is really big for taste and the eyes are really big. And Yeah. So
it's weird, but the only IO on a human that's not on the head is touch.
That's a good point. Yeah.
And I think about that because I think it's important to state. I had this theory that has not proved to be true, but my theory was that the reason Apple bought Beats because the real estate on the head was so valuable because that's where all the IO is. And Beats had figured out how to make cool shit on people's heads that they wanted to wear.
Okay.
And I thought, okay, Apple's going to go onto the head because, we have to get audio, we have to get vision, we have to get, microphones because that's where all the IO is.
Yeah.
And none of that has played out, at least.
Do you think it's a response time back and forth?
There's a latency issue, but then some things, like you want to proxy the senses. That's the winning strategy. Because if you think about like Apple Vision, it gave up on AR, which is trying to overlay an image on the real world. Said too troublesome, give it up. We'll just use cameras, pick up the real world, render whatever we want, and then proxy that into the eyes.
Yeah.
So and then, noise canceling headphones with pass through, which Apple also makes, do that for audio. And that's the winning strategy, at least for now with computers, because we can proxy the senses, then we can augment them with whatever we want with computation.
Right.
And that's working really well in those two right now as example. And so I think where this goes, and this is another totally unproven prediction of mine, which is that in the future, everybody just wears a helmet.
Yeah.
It's not a helmet for protection, but it's just you just stick the helmet on. It's got your microphones, it's got your headphones, it's got your vision, it's got
smell.
And whatever your nose needs and, whatever your mouth needs, but and it can have the battery and it can be balanced and it can be comfortable. And I'm just looking forward to kids wearing helmets and you got retractable mohawks to make them cool. That's the future. And in some sense, I think that would be a better move now than trying to pack everything into glasses, which is extraordinarily hard.
Yeah.
Doesn't really solve all the problems anyway.
Right.
Whereas a helmet isn't that weird. They are weird to wear indoors, but we see people in helmets all the time.
Yeah.
It's more and more common.
Right.
Not just not full motorcycle helmets. You could make basically a super lightweight motorcycle helmet, like a helmet for like a mountain bike is like a couple hundred grams.
Yeah.
And you could get rid of the protection and probably get down to 100 grams.
Yeah.
So the helmet itself is just a little bit of structure,
Right.
but then you could pack all your batteries and sensors and everything in there.
Yeah.
So I think that's
Awesome.
that's got real potential and you have like a retractable visor, can have eye contact if they want.
I drove in wet.
So I think there's I don't know if that's really going to take off, but that's what I think should be the near term thing for something like Apple Vision. Apple should just make a helmet.
Yeah.
Their big problem with Apple Vision is balance anyway, like just out of batteries and freaking people will love it. So if you think about how that stuff all plays out, the truth is we got to proxy the senses basically.
Okay.
And even in the best case scenario, you want to do that because, for vision, if you're in the dark, then you want to be able to, brighten up the room. And for audio,
I thought you were gonna say feeling.
and for feeling, you want to we don't have any of this. Like if you think about what you're working on, the corollary utility is haptics.
Yeah.
It is like, how do you make feel when we want to render feeling?
Yeah.
We aren't very good at that.
No.
We don't have ideas. I think a killer app right now would just be, if you think about like the screen in a Tesla or an iPad, they're very frustrating to use while driving because you don't feel anything.
Right.
You
You have
can't
to
like
look at
slide.
it.
You
Yeah.
can't, in my, 2004 Audi TT, like my body knows where the buttons are.
Yeah.
Because I've had that car for a long time.
Yeah.
And you can feel them. I don't have to look for a button, but you can't do that with a Tesla screen.
Yeah.
And so I think, somebody can figure out how to make a screen with some, some kind of a
Vanishing
programmable
display.
Yeah.
That there's
examples of that.
Yeah. One of my colleagues, Christoph Keplinger, he makes these stretchable capacitors.
Okay.
That you can apply electric fields, and then that the Maxwell stress is what it's called, pulls the plates together and then deforms the dielectric rubber in between.
Oh.
But that requires high voltage, low current.
Yeah.
So actually is safe, and
Okay.
but you need high voltage electronics, which is something that hasn't been developed as well as low voltage electronics. But also, if you replace that dielectric rubber with a dielectric liquid and you have them network together, if you squeeze down here, it inflates over here.
Yeah.
And so you can have, I think he calls them haxels maybe, or somebody calls them haxels. Yeah, but it can be transparent.
Okay.
Every part of that material system can be transparent. And then you can overlay it onto a display.
Okay.
And then create raised things.
So I could have like an iPhone future with like a pop-up thumb board.
Yep.
That sounds good to me.
Yeah.
Seems important to be able to at least do that.
Yeah.
And I think there's got to be utility at least in a Tesla or, cars in general.
Yeah. I think there's this in haptics, which I was in for a little while. I haven't been for a couple of years. The focus was on, should we make a glove or should we make props?
Yeah.
And props are much easier to control.
Yeah.
With less of a lot of variability to it. So I think a lot of people wanted to do props, but obviously Meta had that glove and Axon
Nintendo
VR
had the glove.
Oh, the power glove.
Yeah.
I teach a product design class and I use that in my case study.
Cool.
My case study, the power glove.
I think they're getting hard to get.
I still have it.
Yeah, good. Might be worth something.
Yeah. The problem with that was they released it before they made it compatible with their games.
Oh, really?
There was a delay. And so there's only 2 games that were designed for the power glove.
Oh, wow.
And that works. But every other game, if you're playing somebody with a regular controller, they're doing something like 200 milliseconds faster than you are and just beating you. And
So it wasn't cool.
Yeah.
Yeah.
It looked cool.
Right. It looks cool.
Bad. That was from the Wizard, the movie that featured the glove.
The Wizard?
Yeah, there was a movie called The Wizard that featured the power glove.
Oh, really?
It was like Nintendo's marketing campaign. It was also the most popular movie of the year that year.
Oh,
and the kid in it, in very 90s fashion, had the glove on. He's like, it's so bad. But it meant good at the time.
Back when bad meant good.
Yeah.
For some reason, didn't they have one in like Ready Player One? For some reason, I'm picturing a power glove in there.
I actually haven't seen that one.
Yeah. Okay. Anyway, so the comment made about how like, okay, people want to work on hardware less because they want to do machine learning.
Yeah.
Did you watch the NVIDIA keynote?
I've seen snippets of it, but I didn't watch the whole thing.
You gotta watch it.
Okay.
The NVIDIA keynote is the only thing that matters in the entire world right now.
Holy crap.
Wars in the Middle East don't fucking matter.
Okay.
We will forget they even happened.
Okay.
The only thing we're going to remember.
Yeah. This is the foundational humanoid robot model?
No, none of that. It's just that right now the world has about all in, like all supercomputers, like about 6 exaflops. NVIDIA, and they're like football field size computers.
Yeah.
NVIDIA is shipping an exaflop in a rack
Whoa. Wow. Okay.
the size of a refrigerator.
Wow.
They've got orders for thousands of them.
Wow.
Like we are entering like the zetaflop era, and that inflection point is so massive because for years we've been computationally constrained on things like modeling every cell in your body, all the stuff floating
Right.
around in the blood, muscle fibers, everything. We've been able to sort of simulate it roughly.
Yeah.
We couldn't do everything.
Right.
We couldn't make a realistic
Yeah.
model of you,
Yeah.
much less of everyone. We couldn't model climate effects. We couldn't model for Earth. Like the atmosphere of Earth is literally the one thing bigger than this planet in our world, and we couldn't model it.
Yeah.
We couldn't model every neutron in a nuclear reactor core. Now we can do all that more. And so we're just at this inflection point where now we can
Yeah.
model every single thing in the world in software.
Yeah.
And the value of that, and I'm always preaching about this, is that we can then run those simulations. And the simulations let us test out designs
Yeah.
before we make them in the real world.
Yeah.
So for you, and this
Yeah.
is, I think it's a renaissance moment for
Yeah.
robotics, because now the computer can know everything about all the materials, can know everything about what we want to make.
Yeah.
It can go spend all night trying different designs
Yeah.
for making, actuators or sensors or muscles and trying different materials.
Yeah.
And it can tell us in the morning what's going to work the best.
Right.
And so I think you guys will just be able to get a lot further, a lot faster.
Yeah.
I know it's fun to go build something in the lab, and we want to do that. But now when you go build something in the lab, you'll be building the right thing,
Right.
or something that advances you much further.
Yeah.
And so I think robotics has been held back because it is an area slow and expensive to iterate.
Yeah.
And I think we used computers to help some before, but we are now at a point where there's nothing left to be desired on what the computers can handle.
Yeah.
And so that will make a big difference in the field. And I think, because I do think robotics becomes, I don't know, you could say almost the second most important thing, which is, all right, now we have the brain, where's
Yeah.
the body?
Right.
And that's
Yes.
robotics.
Yeah. Yeah.
And so it's an exciting time.
Yeah.
And this is a case where, you got researchers all over the world. All you guys are fixated on one little issue or another.
Right.
And everybody's going to be coming out with like cooler and cooler shit
Yeah.
and sharing it. So that's pretty exciting.
Yeah. When I saw NVIDIA's Isaac, I was like, okay, yeah, that's how it's going to be done. And now there's the compute power to do it for real.
Yep.
So yeah,
There you go.
It's
Yep.
exciting.
It's super exciting.
And it's exciting for things like retirement homes,
Mhm.
like aging population,
Yeah.
caring,
Yeah, those are really important applications where we don't have the people to take care
Yeah.
of the physical
Yeah, right.
bodies that are deteriorating. It also, but I think like looking further out, I mean, I've been thinking, American healthcare system's so fucked up, literally no chance of fixing it,
yeah.
no matter what we try. So my idea is like, well, if we just cure everything that people have,
Yeah.
we cure all the diseases, we
Yeah.
won't need the healthcare system
Yeah.
except for like gunshot wounds.
Yeah.
Because and it won't matter that it's not fixed. And so I think that should just be the new target. Like,
Yeah.
just cure everything.
I'm all for that.
Yeah.
I'm very confident in our ability to engineer and
Yeah.
science our way out of most problems we have.
Yeah, and a lot of them are just
Relying on politicians to do it isn't the right move.
no, that's the wrong move. Don't use a politician when you can engineer your way out. So, yeah, it's pretty exciting.
We're applying our robots to agriculture a lot.
Okay,
In
good.
that, and the undersoil or the rhizosphere, where the root meets the soil and bacteria and nutrients,
Yeah,
is like completely like nobody studies it because it's so hard. You have to some people study it, soil scientists,
Yeah.
but they have to dig holes and put a little camera down there and take some samples to a GC or
Okay.
mass spec and then do some culture, but it takes so long to do any of that. We're building through this National Science Foundation funded crop center. We're putting these tunnels underground, like in fields,
yeah,
with sort of like when you go to a bank and you put these tubes
Yeah, I
in
know.
and it goes
Yeah.
through. Yeah. So we're setting up tubes to go underground and then capture as the roots are growing, take soil samples, not just from one location every few weeks,
Right.
but from thousands of locations every day.
Mhm. Mhm.
We just created the pod that's
Okay.
going to go in the tubes to do it.
Cool.
And we're hoping to deploy that this.
What about like Z-axis? Does it have
I
them
know.
at different levels? Not yet.
No. I mean, yeah. I want to go there, but
Yeah.
they're just so excited to get
Yeah.
anything. So we have ideas for some fiber optics that'll go up and go through the Z direction,
Oh,
coupled
okay.
with some
yeah, but still, it's
Yeah.
amazing to be
Yeah.
able to get that data and see.
off with this worm time robot that we thought would just be able to control and dig. It's so slow, painfully slow. The auger, soil is. We thought we'd
How
done
do
it.
worms do it? I just don't understand. How does a worm?
They have this. They're kind of like a wide body, and they create a narrow projection, and then push out and create a little crack that they move
Okay.
into. Yeah, and we're too big for that. Like we can't.
Wow.
With the telemetry we need, the hardware is too big to do
Yeah.
it. So we went with an auger. Yeah. There's this other program that RPE is funding to take all the power lines above ground, not all of them, but a
Mhm.
lot of them, move them underground.
Yeah.
And so we took our worm,
Okay.
because even if it does go slow, it's actually still probably less expensive
Oh.
than trenching
Oh.
through. And then we also added a combustion powered head to it, little micro combustion head. So we're trying that out. That might move faster.
Cool.
Yeah.
So you could go,
How it does
you could basically hook it up to a wire.
Yeah.
And then just say,
Yeah.
go drive
Yeah, yeah.
underground, dig a tunnel
Yeah.
of your own,
Right.
drag the wire behind you.
Yeah. Then
Very
nobody
cool.
gets upset, like
Yeah.
their day isn't interrupted. And
Yeah,
then-
that'd be amazing.
yeah.
Think it can
Where's
work
Yeah.
for this thing?
About, I don't know,
Right.
3 centimeters.
3 centimeter diameter.
I think to
So it's
actually
like,
do
it's like the boring
that's our
company,
prototype.
micro
micro boring.
company. It's like
To actually do it, it'll need to be
quite
like
as
5
boring.
inches.
The less boring company.
Yeah, right. 1 millionth as boring.
Yeah. Okay. Cool. Yeah, that seems like it's totally worth doing.
Yeah.
Even just and then maybe like a 1 foot diameter version of that would be
Yeah.
really cool. Go lay sewage pipe.
Mhm.
Just make a boring, like the whole boring company thing, but like diameter
Yeah.
for laying. Like there's all kinds of utility for that.
Mhm.
Interesting.
Yeah.
How to cut up roads.
I think that the reason we think it'll work is we're doing explosions in
Yeah.
a small, explosions are powerful,
Yeah.
but if you try to do it electrically, you can't do it as powerfully as you can with combustion.
Mm-hmm.
And we have these little tiny rubber domes that can move really fast with really high force. And then we think it'll crack.
Huh.
We think we can do what worms do at a larger scale with these events.
Cool.
Yeah, we'll see. I'm really glad RPE exists.
Yeah, me too.
Yeah.
We need like 10 more of those.
Yeah.
ARPA, DARPA. You got
There's an ARPA health.
health. Great.
Yeah.
I got 23 more alphabetic letters we can apply to this. Like, we'll take ARPA X, Y, and Z. Funding cool shit.
Yeah.
What are some other cool robots you've seen?
Well, I'm focused a lot on underwater ones.
Oh.
There's the one I mentioned, the oarfish, but then there's this one that went down to the Marianas Trench.
Oh.
It was made of rubber.
Oh.
So it's, it can be compressed with high pressures and not break.
Okay.
The battery we're making for our oarfish can also do that. So we're planning on taking this really long one and putting it really deep.
Cool.
Yeah.
I have an idea for an underwater robot.
Okay.
So there's currently a problem. We want to start mining the seabed
Yeah.
because there's all these valuable metals down there and they're easy to get because they're just nodules, just like basically metal rocks
Awesome.
laying on the bottom of the ocean.
Okay.
So you just got to go pick them up.
Uh-huh.
And so people are trying to design these underwater mining tools.
Yeah.
Some of them look like giant robots that want to kind of vacuum up the seafloor.
Mhm.
And they can't get them approved because they cause a lot of damage. They
Yes.
can soak up sea life and destroy fish and stuff too.
Okay.
So,
Release methane clathrates.
well, that's also a risk. Yeah. So they're just like, I think they were sort of designed with mining industry sensibilities,
Right.
and that's not going to fly
Right.
with the sort of environmental notions that people have about the oceans.
Yeah.
And that's probably great. So what I'm thinking is something, because this is like 2 miles down, design something like a quadcopter drone water.
Yeah.
So it's small,
Yeah.
consumer scale. You throw the thing in the ocean control it remotely with a PlayStation controller. Modules.
Yeah.
You find one, you pick it up, you put it in a bucket, and you get paid
Awesome.
in Bitcoin for mining.
Awesome.
Because
Mining Bitcoin.
so it's like gamifying this mining.
yeah.
It's valuable. And it's a good thing to do because it offsets mining that's much more environmentally damaging.
Yeah.
But you want to do it in a way that doesn't damage sea life.
Yeah.
So, you got a kid who's bored
Yeah.
playing video games anyway. Now your game is like, go find these nodules. If you hurt any fish, you get like, you lose all your Bitcoin, whatever. And so we'd just be making like hundreds of thousands of these like little drones that
Yeah.
are like sort of economies of scale. They're
Yeah.
cheap. You throw them in the ocean. They run for a month or two before they just die or whatever. And then you get extra points for finding old dead robots and dragging them out of the ocean. I mean, I think it would be cool.
I think so.
Like, let's gamify like doing the stuff that we need to do in the world.
Italy's CNR, I don't remember how to pronounce it. In Italian, they make a robot like what you're describing, not
Okay.
a fly to what you're doing.
Yeah.
But you should talk to them and
But
see
it's
if
a
they'll
deep
do
sea
it.
underwater robot.
Yeah, that has these impellers arranged like quadcopters
Oh.
do it, and yeah,
Great.
yeah. But it's not for mining like you're saying. So
but
just
all we need
put
is
a little
a
gripper on it.
crane claw.
Yeah, right. And then I see all these people, all these high schoolers that are playing video games anyway. Just
Yeah.
have them do that
Right,
instead.
exactly.
I like it.
So you can play GTA or you can get paid,
I'm
work
in.
on your college
All right.
fund. I know. Somebody should build that.
Yeah, run it up the
That's
ladder.
cool. All right, let's get out of here.
Okay.